Okay, let's go. Yeah. Hi everyone. Let's resume the session. So the next speaker is Guillaume Sartoretti. He's from NUS, and his talk is about the advanced in sensing and actuation computation and the communication. The deployment of a large number of robots is becoming promising avenue to enable the speed up of complex tasks in areas such as manufacturing and last mile delivery, search and rescue, or autonomous inspection. And his group is a strive in pushing the boundary of a multi-agent scalability by understanding and eliciting the emergent coordination and cooperation in multi-robot system, as well as in articulated robots. So yeah, without further ado, let me just pass the presentation to Prof. Guillaume.
Yeah. Awesome. Thank you. Thanks, sir. But yeah. Hi, my name is Guillaume. I'm from NUS. And so the idea of today is to talk about multi-agent robotic systems, right? And so this is kind of like the terminology I'm going to be using today, but it's also essentially the outline of the talk, right? So when you look at multi-agent system and multi-robot system in general, you're looking at the different ways of coordinating them, and it goes from weaker to most tight alignment, right? So on the left, you have what we call coordination. So this is using the terminology from Amanda Florock's like recent paper, and I like it, so I'm going to be using this, right? So coordination on the left considers weaker alignment between the agents, so problems like multi-agent path planning, which I'm going to be talking a lot about today. In some cases, when the obstacles are not dense, then agents mostly need to not be in front of each other and not be a problem for each other. So the alignment between the agents is weak is just about not getting in each other's ways. And in this case, you're usually expecting sublinear gains. So as the number of agents goes up, you're not getting like linear speed up in performance. In the middle, you have what I call and what she calls cooperation, which is a lot stronger alignment between the agents. Like the team has one objective and every agent is trying to work towards this objective. Problems like coverage or search, like this one. So you have agents that have limited communication range that have to be deployed from this base station and try to find targets. And in this case, you're trying to find, you're usually finding either super additive or threshold enabled gains. So in this case, for example, if you don't have enough agents, then you cannot solve the task. And as soon as you have enough agents to really create this chain all the way to the target, then immediately you get like 100% success, essentially, in this case. In this case, I'm also going to be talking about joint action selection. So allowing agents to reason about joint actions to complete a problem, right? And the last one, which I'll talk briefly about, is kind of like the holy grail of multi-robot systems. In this case, it's called collaboration. It's considering agents with different abilities that can work together and like identifying synergies and complementarity of abilities. And in this case, you're hoping that you get the 1+1 is larger than 2 regime. So super linear gains. So agents that cannot do something together, but together by themselves, but together are able to do it. So I'll talk about a little bit of each of those things that we've been doing in my lab. So the first one I want to go through is because I was interested, like, the logistic aspect of this workshop is I went through multi-agent pathfinding. So anybody that attended the workshop on MapF this morning, there is a bit of overlap here, but don't worry, there will be a lot of new things as well, right? But so in this case, I consider the problem of MapF, right? So I have a bunch of agents, I have a known environment, and I want to bring those agents to their goal as fast as possible, avoiding collision with the environment and especially with each other. There's ways of approaching this problem. The first one is just go naive A star. So you just extend single agent A star to multi-agent systems, and you consider one meta agent in which you search in the joint configuration space of all the agents. You can do this, it works, but it does not scale well at all. Like this example here on the right has 200 agents. If you're looking one step ahead with each agent having 9 movements, northeast, southwest, diagonals, and stay in place, you don't have enough RAM on the planet to even do one step look ahead in this plan, let alone like find the actual plan, right? Because you have like 9 to the 200, which is essentially a Google squared number of states that you would have to search through. So clearly that's not an option. So the community has been looking initially at decouple approaches. So either velocity planners, I plan individual paths and then I adapt the velocity of the agents to avoid collision, or priority planning, which is, plan for one agent and plan for the second one based on the first one, et cetera, et cetera. They're nice, they scale really well, but they're strongly suboptimal. And that was the big limitation. And so in the middle, we've, for now, the state of the art in search-based planner is dynamically coupled approaches, MSTAR, CBS, LNS, etc. The idea is you're planning for each agent, and then you're finding a way of solving collision by locally increasing the search space. And with always the goal of coming back to single agent planning, which is a lot more scalable. In terms of performance, if you're looking at optimal on the left, this is the number of robots that you can handle with the different approaches. You see A star breaks down immediately. You can actually only do 3 or 4 agents, then it doesn't work. The other ones do a little bit better. But what's really interesting is on the right, you have bounded suboptimal methods. So a lot of those dynamically coupled approaches that allow you to get a suboptimal method, which is a guarantee on the suboptimality level. That is user input. And in this case, with only 5 minutes of planning, you can usually get to about 150 agents. And so that was the state of the art when I started looking at it. And I was like, okay, that's really cool. But also it means that there's really not a big avenue for pushing this a lot further if we don't find another way of approaching it. And so my approach in this case was going to be, I want to go back to those decoupled approaches, but I'd like to approach them with learning to see maybe humans were not so good at finding the right rules, but maybe with data and machine learning, we can find it. So the first approach is that MapF is incredibly symmetric. Every agent is somewhere, wants to go to their goal, avoid collision. So maybe there is this one common strategy to do it. So I'm assuming that there is one common policy for all the agents, and I'm trying to find it. And the cool news is I can try to go for distributed learning, and I can try to find the strategy by leveraging the sum of experience from all the agents. So the more agents I have, the more data I have, the faster I can train them. And then the amazing stuff is that at the end, if I'm right, I can just copy this one strategy onto arbitrarily any number of agents. And I should have like perfect scalability. So of course, in practice, I'm not expecting absolute scalability, but technically very close to it. This is essentially the base of what became like the centralized training, decentralized execution paradigm, right? So we can cheat and centralize info as much as we want during training, as long as what we learn is fully decentralized. That's what we do. The way we do it is we adapt the single agent, like distributed learning algorithms. In this case, I use A3C, but you can use any PPO, A2C, other like variant that are like distributed. And we did a decentralized, a multi-agent version of it where every agent learns by themselves in the same environment. Rewards are coupled for all the agents that have like collaborative rewards per agent. And then at the end of the episode, agents calculate their own gradients, but then they push them to a centralized repo that contains the best common policy for everybody so far. At the end of training, this policy has converged and we can really copy it onto any number of agents. So I'll show you the scalability in 1 second. So the first approach is primal. That's the main one that we did for this first work, right? So in this case, we allow agents to have partial observability of the problem. They have a local field of view around themselves, 11 by 11, I mean, 10 by 10 initially, but 11 by 11 with the agent in the center. We create different channels and we give them high resolution information around themselves, position of obstacles, other agents, their goals, and the goal of that one agent if it is within line of sight. If the goal is not within line of sight, like in this example, then we give them a unit vector with a distance to their goal. So the idea in this case, we're breaking MapF into 2 problems, local collision avoidance with full resolution information and navigation to a desired direction. We train by doing 50% of the episode with just standard ORL with a pretty clever collaborative reward structure that we had to fine tune. And in particular, it penalizes collisions and deadlocks. Like in this case, the red agent here, if it's not moving, would be blocking the blue one from getting to his goal. So in this case, we're allowing the red one to detect and learn that he's blocking the blue one, and then he's getting penalized for this. And that's going to be, teaching it to get off goal. We'll show you in a second. And then the other 50% of the episode, we train by imitation learning. So the idea here is that we have good planners, they're centralized, but maybe we can teach those decentralized agents to exhibit the type of good joint maneuvers that those planners would be able to find. And then at the end, we get a policy that allows agents to get to their goal as fast as possible, avoid collisions, and then stay on their goal, except if they're blocking somebody, in which case they're going to get out of the way. And this is what it looks like. So in this case, we have 5 agents at the top that have to swap with the 5 agents at the bottom. And the only bottleneck they can go through has one agent staying on its goal already in the middle. So if agents were fully selfish, the pink one in the middle would do nothing. He's already on his goal, he's winning the game. So he would just stay there and make the problem impossible. But because they've learned with imitation learning and a collaborative reward structure, this is what happens, right? And you see the pink agent is learning to get out of the way. He's learning that he is a problem where he is, so he just gets out of the way, just do anything. And then at the end, he can come back once the swap has been happening. Those core behaviors we learn out of like very few agents. So this is trained on 8 agents. We can actually copy on much larger team, like 80 agents. And I've highlighted a few places where you could see those collaborative behaviors. So same thing, an agent blocking somebody else on his goal, learning to get out of the way. But you see, like it's not as perfect. Like they need to like find good synchronization, and then at the end, finally it works, right? But you are getting those like cooperative maneuvers out of no communication and decentralized cooperation learning. The cool thing is we can then scale this drastically. And this is an example with 1,000 agents. That was the first time that you could do 1,000 agent swarm, and this was fully learned. Admittedly, this is our best case scenario for a decentralized planner, very open world with a lot of agents, very easy. And for most other planners, it's very difficult because you have a lot of collisions to handle. But for us, we can really do it. And this is like just train on 8 agents, executed on 1,000, which is amazing. In terms of robotics, it's really appealing. We get a reactive policy. Every time step, I use the current state to decide my next action, and I just execute it online. And so, for example, for those robots, even if there's a problem in actuation or localization, they just remake that decision and they end up going where they want. The other really cool stuff is that although they have memory in the network, any drastic change in the system is just handled for free. So right now, fifth agent appears, they just naturally handle. They don't need to, replan or anything. They just plan the next move. And if the new state has an additional agent or agents that, died or broke down, that's not a problem. So that's very appealing for robotics. Now, if we go back to what we wanted to do, what I've shown you right now is an example of coordination. Agents are trying to get, to their goal and not be a problem for each other, but they don't really reason about joint decision. They just exhibit some kind of cooperative patterns, but they don't really learn cooperation. So what we wanted to do is really go at pure cooperation. And so what we've done so far in terms of machine learning is more akin to independent learning. But there are other ways of learning cooperation. So the first one is looking at convention-based learning. So creating structure in the agent by trying to have them learn specific conventions. We did this for Primal too, but I don't have time to go into the details of this. Instead, I wanted to focus on what we did more recently. So one of them is communication learning. So allowing agents to identify, encode, and share important information of their state that they can then use to share their intent, reach a consensus, and really like predict each other. The other one is context-aware decision making. So augmenting the ability of the agent to know much more about the state so they can make more cooperative decisions together. So just augmenting their knowledge in this case. The last one that's grayed out is value decomposition. It's explicitly solving credit assignment, but it's not very, very scalable. So I'm not really looking at this right now. We haven't really looked at it in the lab, right? So in terms of multi-agent path planning, our first work was called Scrimp, and it was adding to the primal structure a communication learning layer. So it looks a bit like this. It's based on transformers for their very scalable nature. Comms learning was very limited to only a few tens of agents before. But if you have something very scalable for the comms, then you can get you can still get like better performance and not a problem with scalability. So we allow agents now to output policy prediction of whether they're blocking somebody else, but also a message. And then at the next time step, this message is coming as an input for all the other agents or your neighbors. We tried the two different options, and it works really, really well. We can go up to 500 agents. In terms of performance, so we're comparing with other methods that looked at ways of improving comms learning on top of Primal, and we're the only ones that can get to very dense scenarios, like you can see on the right, with more than 50% success rate. We're also the only ones that got to 256 and even 500 agents. Now you're getting those really nice patterns where agents are now moving in a very methodical way, just getting out of the way and coming back without doing this very weird, just walk around and then come back later, which is really pleasurable. And then, of course, those things also happen in like a larger scenario. So we've highlighted a few ones. This is with the 32 agents. So comms learning, really good way for agents to share information and really start building this like hive mind of decentralized decision making, but very consensual results. More recently, we've looked at like ways of doing context-aware learning, so allowing agents to reason about a larger notion of states so they can do something interesting. So we've done it first for multi-agent TSP, so traveling salesman problem. So in this case, we have multiple agents. So let's say we have just two agents and we have those cities and they have to go distribute themselves and visit those cities, coverage problem, exploration, right? And so here we're developing a neural network that allows agents to reason about the problem, but also reason about each other so they can make more consensual, like cooperative decision making. So in this case, the first agent is going to be looking at the cities first. So there's going to be like some sort of embedding, some reasoning about the problem. And then also the other agents and it's any other city that the other agent has already decided. So for now, nothing else. And then the green agent will select a city. And then the second one will look at, so the blue agent will look at all the other cities, will look at green and its selection so far, and will make a decision itself. And then agents start moving toward this decision, the selected city. And as soon as one reaches it, then the same problem happens again. And so the green one will look at all the open cities, will look at the blue and its allocation, and then we'll make a decision. And so on and so forth, and we build the system. What is interesting is in terms of neural net, you can actually look at it in terms of like encoding steps that are happening, and agents are learning to encode the different cities that exist in the system, so understand the problem, also understand what other agents are doing, and then merge this together to allow them to understand which other cities other agents are going to, and even make predictions over where they might be going in the future. And you get this kind of like in neurospace kind of allocation and prediction of what each other are doing. And the other advantage is because of the neural structure we used, we get scalability to any number of agents, but also any number of cities without having to retrain the system. In terms of performance, we do pretty much as well and sometimes better than meta-heuristic approaches, even with our greedy approach, as long as the problem is large enough. And then we have a sampling-based approach that is similar to fine-tuning or like local search that does even better, right? And what is really cool is the way we tend to beat tools like OR tools, which are very optimized meta-heuristic, is that we're able to deploy all our agents, whereas OR tools sometimes has to like sacrifice deploying all of them to keep the problem solvable. We've done some work also on multi-robot task allocation. So extending this with the idea of having tasks where multiple agents have to join the same city at the same time. So think, multiple robots having to go somewhere to carry a package or something like this. And in this case, so we're extending this and we're allowing agents to also learn by deploying some sort of is a teacher student or leader follower framework. So in this case, to train really well in this problem, we had to reduce the number of decisions agents are actually allowed to make. We're only learning out of critical decisions and we're forcing other agents to follow them to create the right patterns and then be able to reinforce those. For MapF, we actually look at something similar, but we're allowing like transformer use to encode the entire problem and allow agents to not have only local field of view around their position. So in this case, we're representing the entire world, so the static obstacles as a graph. And then we're allowing agents also to share their local, like immediate decisions to share intent in the form of a Gaussian process. And then we can put all of those into the same structure as alpha, as primal, but with this additional context building of the entire problem. And we're allowing agents to understand the entire world for routing decision, understanding each other for like traffic prediction, and then boosting the performance of the overall network. So you see on the right, alpha is able to solve a problem like this quite quickly, whereas a primal or mappers are just never able to solve it because this really complex structure of the world is kind of too off distribution and too confusing for them to actually be able to do it. And then we did this on robots. And then last thing, so this was like more for the cooperation learning, so comms learning and then context learning. The last thing was looking at problems with heterogeneous agents. So in this case, we're inspired by recent work in exploration, like the perseverance, and then just coverage problem where we have like maybe flying agents, agents on the ground, etc. And the idea is how do we utilize their individual abilities, so motion models, but also maybe sensing abilities? How do we leverage synergies and distribute them well, but also use them together in like search and cooperation, cooperative informative path planning problems, right? And so in this case, we're focusing specifically on coverage problem, and we're looking at ergodic coverage. So in this case, we're assuming that we have a prior in terms of information over the entire domain. And what we'd like is for agents to distribute themselves and cover this domain in proportion to the amount of information that is present. one way to do it for like single agent is through ergodic planning. So we're making, we have a prior, we're making a statistics of where the agent would go with a specific trajectory, and we're trying to optimize the trajectory so its statistic matches with the metric. And we can do this by looking at this metric in the middle and minimizing it. So in this case, because we have a distribution and another distribution, we're going through the Fourier domain. So we're actually mapping both of those distribution in the spectral domain, and we're trying to get those coefficients to match. What is really cool is that those coefficients actually have a meaning. So in this case, when we look at the low frequency coefficient, they correspond to slow, wide area changes in the information map. Whereas the higher frequency coefficient, they look more like details, etc. And so our initial point, like in the first paper, was to look at how those might relate to different motion models and sensing models. Large scale changes might be better suited for large scale sensor with lower resolution, so quickly getting like the big brushes of what's happening in the domain. Whereas the high frequency component, they look more like, high resolution, detailed sensors. And then the same way, like the top one might be better done, or you might be better suited to like cover those like big area changes with an omnidirectional model. But then it would be easier to connect those peaks with like something like a curve constrained robot. And so initially what we showed is that if you have good intuition about the problem and you can distribute those, you actually do get better performance. But then we went further and we said, okay, so what if we let the agents be able to understand their strong suit? So in this case, we're actually allowing agents through different ways of representing the problem to actually understand what they're better at and then distribute themselves over the different frequencies of the domain. So essentially right now we're allowing agents to ask the question, what am I better at? And then also what am I good at and what am I better at than other agents? And then identify where their specific motion and sensing models are better suited so they can distribute themselves and distribute the problem. And as we see at the end, we're actually, so there's one kind of point that would be missing on the, oh, this thing works. Oh yeah, no. There's a point missing. There would be a point here that says, if you use just one agent, you get some performance. If you use multiple agents, you get better performance. But if you distribute them well, you get even better. So we're actually now showing that we're in the range where we have 1 + 1 is larger than 2. Where bringing agents together not only gets you better performance because you have more, but if you actually use their individual abilities and the synergy as well, you actually get even better performance. So you get 2 agents and you have 3 times more performance, which is really cool. So I think in terms of time, we're there. So essentially, the summary here is that you can look at those problems as like, cooperation learning problems, right? And there's a lot of, like logistics, search, et cetera, et cetera. And so what my team has been working on is finding ways for the agents to learn how to do things well together. So initially as a coordination problem, so you're learning this like common cooperative policy. You can train it faster by leveraging experience from all the agents, but also you can like massively deploy it at scale by just copying it on any number of agents. That's really good. If you want to go further, you can actually learn true cooperation. So looking at either through convention or communication learning or augmenting the knowledge of the agents to allow them to really make explicit prediction or explicit joint decision with each other. And then our ultimate goal is to push this towards heterogeneous teams as well. More recently, we've been looking at like ways of boosting this. So either through intent sharing, so allowing agents to use their policy to make prediction of where they might be going and sharing this with other people. So they make the more informed decision about the future. Modeling each other, like really going into either model-based multi-agent RL or at least making like short-term prediction about other people, like, generative models and things like this. And then the last one is abstracting cooperation and looking at strategy learning. So in this case, like extending the concept of skills to multi-agent system and saying, we could be using this strategy and then this one and this one to solve long-term strategic cooperation problems, right? And with this, I mean, this is all of the people that have been involved in all of this work, and I'm happy to answer any question. Yeah, that's
There is company. How do they like what is saying before, how do I extend it and large scale space, which may have thousands of nodes with someone, how do you solve this in real time?
Yeah, that's a really good question. Yeah, yeah. So when you're going for like scalable problems, like large scale problems, you can't predict agents one by one, right? So we're looking at is either a kind of like mean field approaches, like can you represent what the team is imposing on you in terms of constraint, right, or improvement? Or can you look at it as more of a traffic problem and you can predict stuff like, occupation or traffic congestion level in different areas of the world. But you're trying to always like represent the large team as a one kind of distribution problem. Otherwise, you can't do it. There's a good point because like you can predict like one by one other agents or one guy, but you can't predict 1,000, and you definitely can't predict like in a scalable way between 10 and 1,000 agents, right? But if you go through distribution, that's one way of doing it. Yeah.
Yes.
Wait, say again. I'll repeat it afterward.
Yeah.
Okay, that's a very good question.
That is all.
Yes. Okay. Okay. So the question is, I'm repeating for Zuma. The question is like, if we optimize individual reward, how do we look at like optimality of the team level performance, right? Yes. So this is a very good question. So first thing is we don't go for optimality. So that's easy, right? We just look for, can we get good performance, especially in scenarios where there is no other option? Like in a lot of the problems anyway, you can't deploy a better planner. So what I propose is the only way anyway, right? But the bigger question of how do we go from the local to global, right? How do we go from local rewards to global performance? Or how do we go from I want the team to do this to devising good local rewards? And so the short answer is there is no general way, right? We've been like playing with like reward shaping and things like this as much as we can. Imitation learning is another way that you can do it, right? You can say, hey, I can't tell you how like I can't tell you how good or bad a specific thing is, but I can give you demonstrations and you can learn to copy this, right? But in general, the reward shaping aspect is still a tedious kind of manual process that we have to do. So from APF, like we have good intuition and we can try it and we can like, you know, build upon our experience. But if you give me like a new problem, then we always have to play with it a little bit until we get something that seems to work. So yeah, I mean, sadly, a disappointing answer, but it's a good question. I mean, it's a very difficult problem, right? Yeah.
If not, let's thank you. Thank you, the Prof. Guillaume class already. And we will move to the next speaker. Next speaker is Professor Zhou Boyu. And in his talk, he will be talking about the present research on UAV in the area of active perception and mobile memory application in inspection and logistics. So he will first introduce some of our controls to get efficiency in exploring environment, including advancement in real-time planning, efficient environmental representation, and strong collaboration. And then
Everyone, thanks for Dr. Yuan's introduction. And yeah, I'm very excited to share with you our research about autonomous aerial vehicle. And in this lecture, we will explore some of our recent
development in this field. Okay, so first, let me briefly introduce the background. As we can see, UAVs, which means unmanned aerial vehicle, are increasingly popular nowadays. And they are applied to many real-world tasks like we show here aerial photography, structural inspection, precise agriculture, and search and rescue. And this application demands a higher level of autonomy because we can see that in many environments, we require minimum human intervention. In many of these applications, if the environment becomes dynamic and structured, sometimes manual control is impractical. So this is where the needs of high-level autonomy comes. And specifically, we are interested in develop perception, planning, control, and multi-robot coordination method to improve the level of autonomy. And specifically, to fully explore the capability of unmanned aerial vehicle, we find that there are a few critical areas we must address. First is the foundation of everything, the reliable autonomous navigation capability. And then active information acquisition is another key advantage of UAV because they have a higher level of agility. It allows them to gather data from unique viewpoints that traditional ground-based vehicle cannot reach. And third, physical interaction. The aerial robot should not only observe but also learn to interact with the environment, whether it's transport some payload, manipulate object, or even interact with human. Okay, and lastly, in some large-scale environment and very complex tasks, we must explore multi-UAV system so that we can improve the operational efficiency. So the first thing I would like to introduce is our research on motion planning. We focus on addressing the computational constraint of UAV, which limits their weight, size, and power consumption. We know that for a small UAV, typically there are only a small sensor, small computer, so they can have very limited sensing capabilities and computation resource. So one of the biggest challenges in UAV motion planning is how to achieve robust and efficient motion planning with a high success rate. And so when they fly very quickly in a complex environment, they must react typically within milliseconds to match their agility in complex environment. So to solve this challenge, one of our representative work is we can see that in two ways. Just for issue one, we find that many methods typically follow a single trajectory, but we design a topological path planning method to optimize multiple distinct trajectories simultaneously. So you can see in the slide, each path will offer a different approach to avoid obstacles and allow us to optimize several trajectories in parallel. So in this way, we can try to find better solution in parallel, but it does not add extra computation time because we do the computation in parallel. And secondly, we implement an eastline-based trajectory optimization method. So unlike traditional method, we should do the optimization, we enforce the constraint by densely sample many checkpoints along the trajectory and enforce the constraint. However, we can employ the convexful property of the B-spline-based representation, so we can do the basically we can do the computation much more efficiently. Okay, and here we can see the result. The result is that we can fly very quick, very fast in complex environment, and the planning time is typically within a few milliseconds. And this is basically the foundation of navigation, and building upon our foundation in navigation, I would like to extend the discussion to active perception, and typically about the problem of autonomous exploration, which means that we would like to use an autonomous robot to map an unknown area as efficient as possible. And here is also the foundation of many applications, such as we want to do an inspection of bridge or to explore underground cave. Okay, this area are typically hard to assess by human. We can use the flying robot to acquire this information very convenient for human. So autonomous exploration is much more challenging than basic navigation, because when we do basic navigation, we just focus on obstacle avoidance. However, when we do the exploration, we not only navigate, but also select the next destination to maximize the efficiency of data collection. So this will involve an actual process like detecting the boundary of known and unknown space. We name it frontier detection. Okay. So in many traditional approach, they face several critical challenges. The first challenge is that many systems will rely on greedy strategy to do this frontier detection. And another challenge is that many approach will rely on some efficient computation, like they may do the frontier detection within the entire map. And as we explore a large-scale map, it becomes very computational demanding. So this will make the robot respond very slowly to the environmental change. And the third challenge is that we know that for UAV, one of the biggest advantages is that they are very agile. They have flexibility to fly agilely. But if we simply adopt some simple motion planning method, they cannot fully exploit the dynamic capability. So to address the issue we just mentioned, we developed specialized data structure that allow efficient local map processing. This local processing means that we only do up-to-date information, frontier information. We can maintain it incrementally within a very small scale local horizon. We can make everything up to date like we do it globally. And another thing is that we optimize the path in a global manner, unlike previous one, just to do some greedy selection. And finally, by some integration of our advanced motion planning techniques, we can achieve a higher flight efficiency. And we can see some demonstration here. By the advancement in data structure and motion planning, we can enhance the efficiency by about one order of magnitude. And we test our method in many different environments, like the underground cave, some campus, like there's forest or some indoor scene. We can achieve good performance. Okay. So despite the advancement we discussed previously, there are still some mismatch between the goal of the problem itself and the methodology. We know that the goal of exploration is to cover the entire unknown environment, but from the planning method, we only consider the boundary of the known and unknown space, which is the local planning. Exactly. So, how to solve this problem? In one of our recent work, we proposed a framework that uses global coverage paths that span the entire unexplored region. And then, given the guidance of this global path, we formulate a sequential ordering problem. so to make the local motion planning better aligned with the global path intention. So this method will more systematically decompose the exploration problem into two steps. The first step to adapt a real-time mapping perception and to plan a global coverage path that cover the entire space. And then for the local part, we formulate a more reasonable formulation so to make the local trajectory better follow the global path. And from the comparison here, we can see that in some recent approach, we can achieve the sort of performance in both simulation and some real-world experiment. And here are some real-world experiment, like in complex wooden structure and parking lot and artificial indoor space occupied by dense obstacles. Okay. And so far we talked about exploration in a relatively small scale. And recently, one of our work has focused on exploration in large-scale environment using LiDAR sensor. The strength of LiDAR sensor is that it can generate high-precision point cloud map, which contain rich information that's crucial for large-scale navigation. We know that LiDAR point cloud map originally contains sufficient information for navigation. However, we find that many current methods still rely on additional, often expensive environmental representation to do the decision making and to the path planning. Okay, like we already have the point cloud map, but we still need to build the occupancy grid map or some mesh-like structure, like something else to facilitate the navigation. That's actually some extra redundant information besides the point cloud. So our point is that whether we can do all the decision making, do the navigation on the point cloud. So this is our recent work we propose a framework named EPIC, which is the abbreviation of exploring on point cloud. In this structure, in this framework, we can do all the frontier detection and the global path planning, all relies on some lightweight data that is accompanying to the point cloud without any other complex data structure. And here are some results. You can see that we can explore some large-scale scene like a few thousand square meters. However, everything we use is just the original point cloud generated by the point cloud, by the LiDAR sensor, and we didn't need anything else to do the path planning. And importantly, everything can do in a comparable way, like the previous method. In terms of efficiency and in terms of flight velocity and exploration time, we can do it even better because we save many computation resources to do the planning better, quicker. Okay. So in the previous section, we tackled the challenge about exploration in the small space, tight space. But when we expand to large environment, typically spanning tens of thousands of square meters, a single UAV may not address the problem very well. So we need collaborative exploration, where multiple UAV work together to cover the area more efficiently. However, we find that traditional multi-UAV methods come with their whole set of problems in terms of in the context of exploration. One is about the efficiency side, and then another one is about the requirement of communication. From the efficiency side, we find that the most critical module, the task allocation of exploration, often focus only on some frontier area. This is actually very similar to the issue we mentioned before. We are actually want to cover the entire space, but when we do the task allocation, we just consider the frontier region, which is the gap between the target and the problem formulation. And from the communication side, we find that actually to do the allocation of exploration tasks, many methods will rely on a global communication or a very strict requirement of synchronic among the local communication. So this will make those systems less reliable in real world when the communication range or the bandwidth is very limited. Okay, so how to solve this issue? We propose a framework named reason to address it. And the first thing is that we represent the workload in a more reasonable way. We do the space decomposition with a hierarchical data structure to break down the entire unknown region into some sub-region that can be transmitted among the vehicle with very lightweight communication requirement. And the second thing, we propose a mechanism that can do the task allocation with minimum communication requirement. So this strategy then pairwise interaction require only a synchronous and unreliable communication between each pair of nearby robots. By repeatedly exchange the task element among nearby robots again and again, we can produce a result that is very similar to a global centralized coordination, but the requirement of communication is much more practical. Okay, and then by formulate a vehicle routing problem in the team, we can achieve a more reasonable growth path for the team. So here are some results. We validate our approach through many simulations and also many real-world experiments. In the simulation, we can see that we can successfully explore complex environments like multi-story building and some large-scale things like a 10,000 square meter maze. And in real-world tests, a team of several UAV can explore both the indoor and outdoor environment, achieve full coverage in minimum time. Okay. So far we discussed the problem of autonomous exploration, and next I would like to share with you one of our recent applications in the industry. But here we apply our autonomous system into an underground cave. And in this case, we can see that after some time, the communication between the remote controller and the UAV are actually disrupted, and we cannot see anything from the human side. But based on our autonomous system, you can do the path planning and mapping fully autonomously. And after a few minutes mapping and navigation, we come back with the rich critical information of the entire underground cave. And the scale of the cave is like tens of meters. Okay. So in the previous discussion, we talked so much about the exploration, and now we would like to shift the focus to aerial coverage. This topic very similar to exploration, but it has its unique challenge. So here are some things. It comes from a recently very famous game named Black Myth in China. Okay, we can see that actually many things it comes from the real world. So how to do this? Actually, we can use autonomous robot to acquire this 3D information and develop it into the game engine, do some 3D editing, so we can get some very realistic things. And okay, so what's the difference to exploration? Exploration is like we ask the robot to wander freely and map everything within a defined space. It doesn't know exactly if you will find, but the goal is to leave everything unturned within the boundary. But on the other hand, aerial coverage is much more focused. Its mission is to precisely cover a specific target like a building and then scan the surface of a building. So this problem has been studied extensively, but it remains complex due to the lengthy procedure and heavy reliance of data. So we can see some previous work, it required a tedious pre-scanning process, which means that we set a predefined task to build a cost model of some 3D structure, and then we do the replanning and perform scanning for the second one. And some other work can use satellite image, and it combined with some CAD editing, we can create a cost model first, and then we do the planning, perform the scanning. Okay, all these processes are actually very tedious and lengthy, which leads to unsatisfactory test efficiency. So our question is, can we use the autonomous exploration method to solve this 3D coverage problem? So actually, this sounds reasonable, but not that easy, because large buildings spanning hundreds of meters require many exploration time, and much of the time are actually spent to some empty space that provide little information that's useful for our coverage. So we need to be much more focused to the specific target. So to overcome this efficiency, to overcome the inefficiency, we have developed a framework using prediction. We name it a prediction enhanced spanning method. So in this method, we include a surface prediction module that forecasts the structure of target area based on some incomplete and real-time map. So based on this, you can see that based on this prediction, we can do online task planning. So this process is very similar to humans infer the entire structure from limited observation based on the human's previous knowledge of the real-world scenario. Okay, so based on this predictive guidance, we can perform dynamic task planning. We can dynamically adjust the flight path based on which part is still incomplete. Okay, so while we see that the predictive method seems to be a promising way, its reliability is an issue. Yes, because we must ensure that the prediction is correct or is informative for the task planning. So one of our recent research is to use multimodal data to improve the prediction result. And here we already developed a diverse data set across various types of buildings. And we decided this workflow. It has published recently. Okay, and based on the prediction model, covering the complex 3D structure is also a very difficult problem. It requires generate thousands of viewpoints and then do the sequence to determine the optimal sequence of those viewpoints. Okay. So in many previous approach, we find that actually the process is not that efficient. We need to do the manual preprocessing, which means that we're giving a model, we should use manual leveling to determine the internal side and outer side, which is the white space for the error robot. And the other thing is that when we do the viewpoint sampling, actually many of those viewpoints are not useful. Many of them are redundant. And for the last thing, given the large number of viewpoints, the task planning becomes combinatorially complex. We cannot solve it for real time. Okay. So our solution is to propose a skeleton-based planning. You can see here we do a skeleton planning extract the skeleton inside the complex structure. And then with this complex skeleton, we can determine the inner and outer space of the complex structure automatically without any manual level. And then based on this skeleton, we can further do the space decomposition. We decompose the complex structure into several parts, and each part becomes some very simple geometry primitive, like the cube or cylinder. So within each of these subregions, we can do the viewpoint sampling and path planning much efficiency, with higher efficiency. And then we concave each part, paths from each part together from a global path. And here we see some results. We do the demonstration here in a famous Singapore hotel. Okay. And we also try many other and to examine our method, we also conduct real-world experiments. Okay. So now, again, when we like to explore the larger area, complex-3D environment with a single zone is a difficult task. So we shift our attention to multi-robot system. And as just mentioned, we can use a team of heterogeneous 3D system, which combine the strengths of different types of zones together. So in this system, we have two types of different zones. One is a LiDAR equipped UAV, which can quickly scan the entire area. So it provides a surface geometry information to create a cost model. This is serve as a global guidance. And then you can find that there are some other types of UAV equipped with camera. And this type of drone will do the detailed scanning based on the cost model. Okay. So in practice, the LiDAR-equipped UAV can efficiently map the entire surface of the structure. And then the camera UAV distribute the text to the allocation of line, and then capture necessary visual information. And then finally, they can generate the reconstruction using the light capture image. Okay. So let me briefly summarize the discussed research. First, we investigate the basic navigation capability, and then we strip our focus to autonomous exploration, which is the foundation of many real-world applications. And then we discuss a specific case, the 3D aerial coverage, which require more focused information gathering of some specific target. And in all this program, we discuss the utilization multi-UAV collaboration, which can boost the efficiency of the entire task. Okay, thank you.
Is there any question from audience?
Question. Actually, we don't project the 3D information to a 2D space. We do everything in 3D space. Okay, actually all the frontier detection and the mapping are from a 3D space. Okay, so it can generalize to any random 3D environment, like hallways or a multi-story building. That's okay, that's fine. Yeah, that's also a good point. Actually, if we only use the polygon information without anything else, it's very difficult to distinguish the case you just mentioned, because you cannot just say that, okay, there's a large frontier in the sky and we simply don't move that way. That's not reasonable, because in other cases, it may be in the sky. After some exploration, you can find something that is important. Yeah. So I think the solution may be you can integrate some other information like vision or semantic. Then you can determine whether the direction of exploration is important or not. And if that's not important, just abandon. Yeah.
Is there any other question? We can have one more question.
Yeah, actually, if the drip becomes very severe, it will have issue to the planet. Like typically we do visual visualization, and when we go a long way and back, if the drip becomes severe, the net distortion will become very large, and it may even block the way back. Okay, that's one example. Yeah. So in terms of perception, we really need some ways to correct. Yeah. Actually, both. In some indoor scenario, we will use vision, but the scale is not very large, like hundreds of square meter. So the drip is not that severe. Yeah. So in some large scale outdoor environment, we can use LiDAR. Yeah. The drip is typically under a few centimeters. That's acceptable setting. Yes.
Thanks for Prof shows nice presentation. So we'll move to next speaker, Prof.
Okay. Cables. Okay.
Okay. Sorry for the waiting, and now let's begin. Okay. Okay. Hello everyone. Today I'm honored to stand here and share some of our recent research on swarm planning and estimation. First of all, I'd like to thank for the invitation and introduction of Dr. Yuan. Should I mute my computer so I can hear the voice in the screen? Okay, or in your mute. I will try to speed up my talk so I won't let you guys miss the welcome reception. Okay. And first of all, let's look at this video. For decades, our researchers are trying to replicate the swarm intelligence of natural creatures to human-made human-made flying machines. But until now, we still can't realize such intelligence with aerial swarm flying robots. Okay, and how to find the answers from nature? In today's talk, I will try to explain some of our thinkings in these three aspects, includes onboard perception, autonomous planning, and also the swarm intelligence. Okay, the first part, autonomous perception. We can see from these slides for the bird, such as a hawk, the eagle, it has some very sharp eye, and it can combine its stereo vision with some instantaneous motion response. For example, the angle such as the IMU in just like the IMU in the autopilot to estimate the real-time angular velocity and acceleration. In this way, the eagle can find its target even from very far distance, and also it can just estimate its pose and position in some open 3D space. And inspired from this, also in the aero robot, we equipped with Zhou with the stereo cameras and also the initial measurements inside the autopilot. Okay, and here are some examples of how we have done in recent years. We developed some algorithms. For example, the first one, we combine some deep learning methods with the dynamic model of the quadrilateral. So we can use only the MU and the measurement of the real-time RPM of the quadrilateral to get the state estimation, even without a camera or the ladder. And also we deploy the real-time omnidirectional 3D perception with onboard computer resources. So for the quadrilateral, we can use its omnidirectional cameras, get its surrounding depth, and also at the same time building the full dense 3D maps. And at the right-hand side in this slide, I show some recent applications in collaboration with Professor Boyu, Zhou, and we have tested our drones to fly with fully autonomy in the underground scenarios. And in these scenarios, our drone can do the inspection and mapping without any prior information and also without any human operation. Okay. And also, we are trying to combine the event camera, the dynamic sensing new sensors with traditional ways to help enhance the sensing capability of quadrilaters in dynamic environments. For example, we have shown some recent results for the drones which equipped with event camera to avoid fast-moving dynamic objects. And also recently, we have published a paper at Stanford Robotics where we propose a new event camera named Macrosarcade inspired event camera. Here we just let the lens of the event camera to rotate periodically, and in this way, the generated images in the generated images, the intensity is much more sharper than compared with the traditional standard event camera. So with our new proposed sensor, in almost every event-based vision applications, we can achieve a better results. And also we are starting the lateral implantation of the quadrilateral, which we want to let it to understand, to better understand the surrounding complex environment with as little computational resources as possible. So since I was doing my PhD study, we are trying to carve some free space around the quadrilateral, around the flying robot to represent its flyable space named flight corridor. And recently we have submitted a paper to H3 Translation Robotics, where we just use low-dimensional linear programming and SOCP, which means the second order cone programming. In this way, compared to the state-of-the-art local collision-free polytope-like space carving method, the IROS proposed in the Rusty Jack's group, we can have significant improvements computational efficiency. And for example, for the 2D application for the ground vehicle, we can generate the general collision-free polytope in within 1 millisecond. And also for some complicated 3D scenarios, for example, for this projector carrying a 3D mini LiDAR, it will fly fast in a forest, and it will generate more than 20,000 pounds around the Zhou where it is flying. And our algorithm can still generate the collision-free polytope in real time. And all this polytope will consist of a flight corridor to support the following trajectory generation and control. And okay, for the second part of autonomous planning, we can see from these videos in nature, there are two ways for the creature to avoid collision. The first one is for the insects. It has very small brain and it can only do some close observation, but it can still do the reactive obstacle avoidance. And also for the birds, for example, for the hawk, it has a large brain capacity and it can observe in far distance. So they will do the trajectory planning, and so they can fly smoothly and fastly directly towards the target. So for quadrilateral, for the air vehicle, we want our robots to fly smoothly and smartly like this bird. And here are two milestone works in my group. The first one is the Eagle Planner proposed, published at IEL, and the second one is the Minko Derivative class, published at Transaction Robotics. In these two works, we solve some problems, some fundamental problems about how to cut off all the redundancy in the mapping and local planning loop. And as a result, in the Eagle Planner work, we can let the Zhou to generate a local trajectory within 1 or 2 milliseconds. And for the second work, the Minko trajectory planner, we just propose some nonlinear mapping and also some constraint elimination strategy to let the robots can solve space and time coupled complicated multi-constraint nonlinear programmed trajectory generation method in real time. And recently we are trying to continuously pushing the boundary of the real-time full state trajectory generation for quadcopters. And here we are, I'm presenting this work unlocking the aerobatic potential of quadcopters. Here we just solve a very fundamental but straightforward problem that how to let the quadrilateral to fly aerobatic movements like some elite human pilot, professional pilot. In this paper, we saw some technical problems. For example, we introduced Hall vibration to cancel the singularity when calculating the desired pose during the trajectory evaluation. And also we do some control work to let the drone smoothly adjust its yaw angle during the flip. And here are some typical results. And here is a drone carrying a LiDAR without GPS and without human operation. It is flying with full autonomy. It flips 360 degrees, and at the same time, the drone has to avoid any possible collisions during the flight. And also recently, we compared our algorithm with some very professional human pilot. Here, this boy, he's the champion of many drone racing games. Also, he is in the national drone racing team of China. And here is a comparison between our algorithm with this guy. As you can see from these videos, although human also can finish these challenges. You can manually command the drone to flip around in circles, but it has many sharp turning, and the generated trajectory is kind of jerky compared to the algorithm. That's obvious because our algorithm can generate the mathematically optimal, the most smooth one, the most smooth trajectory for a drone to fly. But the human is all depend on his sense and his memory and his skills. So the proposed system is a mathematical solution. We think now we can beat the human champion in these challenging scenarios. And here are the results. And also, recently we are doing some end-to-end method of trying to embed the neural network in our planning pipeline. Here, I want to share some of our recent thinking about how to generate trajectory with stable time. If someone familiar with Hybrid A star or any other dynamic feasible trajectory planner in the full state space of a robot, you may find that if you have a very empty space, have a very empty map, your algorithm will finish in a very short time. But if you try to apply your algorithm in a maze-like environment, for example, there are many obstacles in the map, your algorithm will run a much faster, longer time. That's because in the search space, the computational burden is like exponential. So you have to spend a lot of time to find a feasible solution. But if you want to solve this problem in an AI way, there may be new solutions, new possibilities. We can find that nowadays there are many AI-powered engines. For example, you can just enter in some keywords and the network will predict a picture, right? Such as Midjourney and other software. So we are thinking that if we have a 2D picture here, we only currently we only consider the planning for 2D case. So if we have a 2D picture, there are some colors blocks on it. These colors indicate the obstacles. So we just want the network to draw a curve inside this picture. So we think it's much simpler than to let the AI to generate a brand new picture, a brand new cartoon, etc. So we train the network and we find it just works, okay? Of course, we should collect some data. We should generate randomly some typical environments, such as a maze-like environment, such as a forest, and then we just train the network, of course, with some tricks in the training. And also for the generated results of the network, it cannot be perfectly obstacle-free. So we have to combine with some traditional methods. Of course, that's which we are very familiar with. So to fine-tune the generated output of the network to let the final trajectory be executable and near optimal for the robot to execute. Here are some examples. We apply the methods, systems the system consists of the front-end neural network planner and the back-end numerical optimizer to fine-tune it. We apply our system to different robots. For example, ground robots with different kinematic models, such as bicycle model and Aquaman models, and also we apply it to fixed-wing aircraft. We found that we can have very, very good results, and in this way, of course, we can generate the trajectory. Actually, we call it depict the trajectory, just like drawing a picture, we depict it, not optimize it, with very stable time. So no matter you enter in a very empty map or very challenging map, for example, as this video showing the, sorry, let's replay it. As the video shows, this is a previously unseen, untrained maze-like environment for the ground robot. We can still directly output the global trajectory for the backend to optimize it. Okay. And so I think I should speed up. And also we are doing some some truly end-to-end quadratic autonomous navigation research. Here we propose optimization embedded neural network, which takes in the images and the history states and the start and go states of the Zhou as input, and with the supervision of primitive laboratory, with a primitive library, we will online predict some flight corridor for the embedded optimizer to optimize the trajectory. So in this way, it's not just a neural network to take in the images and predict the control commands, but we take in the images and history states, and also we encode trajectory optimizer, just like the traditional trajectory optimizer into the neural network. We can let the derivative, let the gradient flow from the network, from the input of the network to the embedded optimization layer. So in this way, we can generate safety assured trajectory with this end-to-end pipeline. And here are some results. This paper has recently been submitted to ACLEAR, and we are going to release all the source code as well as the testing environment and also the data set. So we think our method can be fast deployable. So if you want to try the pre-trained model in forest, you can quickly deploy it. And if you can try it in different kind of scenarios, you just randomly generate some data with some typical characteristics. Okay. And finally, it goes to the swarm intelligence. And we can see in nature, we have different kinds of swarm of birds, swarm of insects, swarm of fish, etc. And for the flying robots, we are trying to build a really smart, decentralized swarm system. For example, as we can see from these birds flocking in the nature, of course, they don't have foundation model. They don't have cloud computing. They don't have ground station. They don't have prior map, okay? And of course, they don't have human operation. So how can we design our swarms, robotics flying swarm, to let our flying machine comparable to the nature creatures? So the most underlying idea, so things is a 2 years ago paper in our group, so I won't spend too much time on the details. And the key idea is design a fully decentralized architecture to let even some agents crashes or broke during the flight, the rest of them can still finish their mission. So each one in the swarm is a very, very smart agent with full autonomy. Okay. So that's a key of our the system. Okay, and here are some experiments showing the team flying in a dense bamboo forest, and also the collaborative tracking, and also in the simulation, and also in the dynamic environments position swapping. Okay, and recently also there we can use our team of decentralized flying swarm to show the formation planning. We can design a desired desired formation, and our algorithm can calculate the best desired trajectory for each zone, and also, of course, it's fully decentralized. And recently, we are trying to push the scale of the planning. So we try to develop some ultra lightweight and scalable planner. Here, scalable means we won't let anything being computed on board and real time. We just pre-compute some trajectories to perform a trajectory library, and this library is index with respect to time and space, and it can be copy and paste. So we just only for each zone, it just only need to store one in I think 100 megabit the memory. So it can still be applicable to a large team. Okay, and here are some results. Of course, in simulation, because we want to test the swarm of 1,000 zones, we cannot try it in real world. And in this simulation, we can see from this video, there are all obstacles but are previously unknown to these zones. And all these short curves represent a trajectory of one zone, and each of the zones should swap their positions. So they are flying towards the center of this map. And as we check the close-up, you can see they're flying towards each other, and the trajectories will be safe. They will avoid any possible collisions with obstacles and also with each other. Okay. They just pass by each other and continue its flight towards the final target. Okay. And also, this paper is currently being under review, reviewed in transactional robotics, and we will open source our code once it's accepted. And that's all. Thanks for the listening. You mean how to control the zone in the racing scenario? Yeah. Space flights, flights. Like. We just control the angular velocity and angular velocity of the zone, and also the total thrust of the zone. That's enough for combining them to do the aggressive flight. Sorry, I can't get your point. What's the question? You mean how to solve the engineering work, to let them all work together? I think we have to do a lot of dirty works to building the Zhou. So every PhD student in my group, I request them to be a qualified software engineer, and we do a lot of engineering efforts. So to test and to review the code and do unit tests and try to push to every piece of the code to its limit. So when we push all of them together, they can show up some good performance. Yeah, of course, in some very fast motion, may have some motion blur in the image. We'll have, and the too fast motion will let you have a very limited time to finish your downstream calculation. So it's very challenging. And in this way, we are trying to combine some learning method with traditional VLO. I think it's a too too basic fundamental components in the VL is the front end, how to process the visual features, and the back end, how to optimize it. For the back end, we now use the filter-based method. For the optimization based such as Vince, it will solve the nonlinear optimization. So it's kind of unstable, especially in the fast speed, but the filter is stable and cheap. And for the front end, we are trying to use neural network-based method to get some deeper features for better backend utilize. I think too many questions to save time. I think we may talk later after the workshop. Okay. Okay, one more. No, at that time, all stuff is model-based. Yeah, for the 2022 Sartoretti's paper, right? It's all model-based. Except for the Zhou detection, we use YOLO to do the detection, and except that all other modules are model-based. You found a problem. Oh, I will blame my PhD student. I think that can be deployed and run in 3 minutes. If you find some problem, you can raise an issue in the GitHub. We will try to fix it as quickly as possible. It's a feature, not a bug, right? Okay. That's a way how to deploy, how to implement a star algorithm. And I think for that swarm playground, a star is just a small piece of it to get some guidance path to go around obstacle for the Eagle planner, right? So it's not very important. You can replace it with your own local planner, such as some sampling based one. And try to use some RT based. It has any time properties, so you can cut off the computing process at any time. If we will at least get a feasible solution, it's enough to get the optimization, because the final solution is guaranteed by the optimizer, not the front end path planner. Okay, that's it. Thanks, John.
Supporting. Oh, sorry. Thanks for talking about.
Shanghai, you are mute. You are muted. Okay, now
Okay.
unmuted.
Now you can hear me?
Yes.
Okay. So yeah, we finished most of the sector. Now is the come to the our challenges award. In this year, this team XMU Mac wins the championship award for the multi UAV inspection task, and yeah, so they actually come and join our competition last year, and they won the fourth last year, and this year they improved their algorithm in terms of robustness, in terms of efficiency, and in terms of everything, and they beat last year's champion by I would say 10 to 20% in terms of score. That means they are more efficient and more robust. And let's give a round of applause to the champion, and I will give him the certificate. Come here and take the Okay, we will spend about 20 minutes time to hear the champion team's methodology, and let's go here. Okay, Zhao Bongwei, are you there?
Okay, I'm here.
Okay, you go ahead and present your slides.
Okay.
Okay, can you share your screen? Yes.
Okay, can you see that?
Okay, half a second. Okay, yeah, I can see you. So go ahead.
Okay, good afternoon. I'm Zhao Bangwei from Xiamen University. I will share our solution of CRI competition here. This is the content of my presentation. First, I will introduce ourselves. We come from Xiamen University, which is located at Xiamen, Fujian Province. It's very beautiful and welcome here. This is a photo of our team. From the left to right is Zheng Yiwei, Wang Yiqun, our advisor Yu Xiao, Tang Can, Mi, Guo Jiarui, and Chen Xianglin. First, I will let me introduce the background of this problem. This is an inspection problem, and we need to capture images on the surface of the buildings at the best possible quality. The UAV fleet contains inspectors and photographers. Only the inspectors will carry some lidars, and they can construct a map. The photographers could only take photos, and they need the information from inspectors. Also, the fleet can communicate, the UAVs can communicate with each other if and only if they in loss of each other. The right video is a screen recording of the MBS scenario of our solution. In the installation step, we divide the bounding boxes into face points and inner points to construct the map. And we use grid map with undetected points, obstacles, and other properties, and octo map to construct the grid map from the LiDAR information. The explorer section points are uniformly sampled within and around the bounding box. We will let the explorers to travel all these points. Also, we will remove some meaningless points before we travel it. In order to move along with the building, we move the explorable points to the obstacle center around it and then we can go along with the building and get more get a better inspection performance. After getting the LiDAR information, we just set all the face points in the bounding boxes as undetected interest points. These points will be set as detected if they are inside of the UAV for some frames. In order to travel all the searchable points, we use a heuristic function containing 4 items. For the first item, we want the UAV to go to somewhere where there are more undetected points, and for the second part, we want the two explorers to be far away from each other so they can explore more about the environment. For the third part of the heuristic, we want the explorer do not plan a path too long at once. The last item for the last item, we want the explorer to go to the position that's we want the explorers to go closer to the photographers, which is not take off to offer more feasible map for them to take off. Also, we will remove some points if it is obstacle or no obstacle around it. And after all the points we have been traveled, we will retravel some of them. For the path planning part, we just use a star to get a collision-free waypoints, and then we use a minion snap or minion jerk algorithm to get a smooth enough trajectory. To go along with the building all the time, we will move some key points of the way of the trajectory along with the obstacle, and finally we will check the trajectory if it is collision free. If not, we will set some waypoints as forbidden and replan to get all-time safe path. For the gimbal camera control, we control the gimbal pitch together with the UAV, the yaw of UAV with a greedy method. We just fix to the mass center of undetected points around it, and ignore those invisible points. In this figure, we face to the orange, the mass center of the orange points, but we ignore the yellow ones. For the community part, the inspectors should get the initial map constructed by the bounding box from the GCS and the positions from other UAVs. Since the photographers cannot perceive the environment, so the explorers should send the grid map to the other UAVs for their motion planning. Also, it should send some other task related information to the photographers. That's the policy of the explorer. And for the photographers, we need them to enhance the inspection results of the explorers. First, we allocate the tasks. In this photo, in this figure, the orange points are undetected interest points from the explorers. We cluster the undetected interest points to two or three cluster, and assign the clusters based on the priority, which means we some points will be allocated to UAV1 and some will be allocated to UAV2. After that, since there are too many interest points in the world, we should and in a, and there will be many interest points in the set of the UAV at the same time. So we downsamples the points and to get a reasonable dance. And furthermore, we will divide the tasks using a twofold cluster to reduce the to make the trajectory more smooth. If they got sufficient more undetected points or after a certain long enough time, the photographers should cluster again and allocate the task again. For the trajectory planning part, we for every undetected interest points, we find a feasible viewpoint around it. And this feasible point is safe and maintain a certain distance to the undetected interest points. To travel all the viewpoints, we firstly find a path to directly connect all the points, and if there are obstacles between any two viewpoints, we will use a star to find a new path, and finally use Minus map or Minus draft to get a smooth trajectory. The gimbal control of the photographer is the same as the explorers. The pitch of the gimbal and the UAV, the yaw of the UAV together towards to the next targeted interest point. In the communication part, they receive maps from explorers and they send interested points and task allocation results to each other, and they share those positions. Also, the messages should be emerged under a certain policy. Some we use some message we use newer, some message we use which is detected, which is occupied. For the collision avoidance part, we have got a collision free to the collision free trajectory to the obstacles. Furthermore, we need to do some collision free. We need to do some collision avoidance policy between the UAV fleets. First, we do a far away from each other strategy by heuristic functions and task allocation. And if two UAVs are too closer, we use a priority-based attitude avoidance strategy. That means the UAVs will fly on different attitude. For the future work, we want to control the UAV with velocity and acceleration to reduce the unexpected maneuvering and do better collision avoidance to get a better collision avoidance performance. Also, we want to control the gimbal together with the UAV movement to get higher quality of the photos. At last, we want to know how and how much we can use the bounding box to accelerate the process. And that's all, and thank you for listening. You are mute. I can't hear you.
Okay, so yeah, if there's no more questions, we'll move to the final section of this workshop. Thanks, bye. Oh, let's just close. So, okay. So for the workshop best poster presentation award, and it goes to Michael Weiner for the autonomous multi-UAV localization of the ionizing radiation source using miniature competent cameras. So can I have all, and thank you for coming today, and okay, take your time. Okay, yeah, thank you all for coming today, and yeah, we have a wonderful section today, so thank you. Bye bye.